Okay, good afternoon, everyone. So I'm going to talk about going faster, but in terms of trying to make mission faster and use some of my past experience. So what I will say is really my own experience and doesn't mean I know the whole truth, but just some indications. So first, I give the conclusion in case I run out of time because I'm usually very talkative. So first, I want to say that exploring new worlds is really fascinating and a source of amazing feelings. And the reason why I say that is because this really allows us to tackle big challenges when we are working, in a team with a team spirit, with the same excitement, the same motivation. I've seen that in the past mission in which I was involved. You can really solve many, many big issues that you realize once you get where you are, because you basically discover new worlds when you explore with these missions. And therefore, this is the spirit you have to have in order to tackle the great challenges. And we are able to do that in space. So it's really, I think, a very positive and optimistic for the future. Then, from my experience also, having a continuous interaction with engineers when you're in scientists and vice versa is very important, because then you understand each other, you can solve problems together better, they understand better the science requirements for the engineers, we understand better the engineering constraints for the scientists, and sometimes in some program you are not allowed to talk directly to the engineers and you lose a lot of time. So I think that's a very important thing to do. Of course, leveraging from past concept studies. In the space agency, we do a lot of concept studies that eventually go nowhere because there is no support, etc. So try to make good studies so that when you are at the proposal stage, you have already a very mature proposal that allows you to save time for the next phases. Of course, the use of CubeSats is very nice because you can take more risk, and in general, taking more risk is essential because more risks means less cost and more missions, and I will show you some examples. Also building on flight-proven platforms, so when you have a platform that worked already in space, reusing it, I will show you one of the ideas, can be a very good thing. And finally, we'll talk about the rest a little further. So talking about exploration, so I'm a small body guy, I'm a small guy too, so that works well. This is really exploration because from Earth, asteroids are just point sources. And therefore, you don't have the knowledge that you can get when you are going there. And therefore, the first time you see the images of an asteroid when you get there is absolutely crazy because they work in a very different environment than the one on Earth. They show an amazing amount of diversity in terms of shapes, sizes, as you can see here, morphologies, composition, of course. And even on one object, you can have a wide variety of geological features, from landslides to boulder fields, to ejection of particles, to craters, grooves, etc. So for a geologist, it's fascinating. But because they work in a very different environment in terms of gravity than Earth, they are very counterintuitive in their behavior, because obviously our experience is based on what we see on Earth. And what we also realize that images do not tell everything. If you want, for instance, to mine an asteroid or to take a sample, it's very difficult to know a priori what will be the mechanical response. And we have seen in past missions that unless you touch, you can hardly predict the response. So that's a very big challenge for the engineer, because they have to develop tools that must be able to cope with a wide variety of surfaces, because from the Earth, you have absolutely no idea what you're going to find out. So an example of a fast success actually comes from the Hayabusa mission, which was launched in 2003 and which got back some samples from an asteroid called Itokawa in 2010. And yet, as you can see on this little manga drawing, the spacecraft was in a good shape. When it came back, there were a lot of failures, a lot of problems, and yet samples were returned. And this is the reason why it took only 4 years, and actually the approval of Hayabusa 2 was even later. It took only 4 years to launch a new mission, which this time was entirely successful. So you learn from your mistakes, and by trial and errors, eventually, within, let's say, 2003 to 2014, so 10 years, you have 2 missions. You launched 10 years afterwards the first mission, the second one, and with a series of very complex operations, they were able to return the samples in December 2020, with also some additional component, but a platform that was essentially the one of Hayabusa 1, and the sampling mechanism that never worked on Hayabusa 1 worked this time on Hayabusa 2. So taking risks, accepting failures, and learning from them allow you to have 2 missions in a time scale which is very, very short compared to usual time scales. So another example is planetary defense, where eventually, if we have an object coming to us, we may have to do these things quickly, otherwise we may be in trouble. So an example is given by DART and HERA. So I will tell you shortly about the story of these missions, which, although they took time, eventually you will see why. So as you know, DART was absolutely successful to deflect the small moon of a binary asteroid on the 26th of September 2022. I show you here a movie where we discovered in real the shape and the morphology of the small moon just 2 minutes before the impact, basically. Here we are 4 minutes ago, and you just start to see how the small moon called Dimorphos looks like. We only had the size before. And at about 6 kilometers per second, a 570 kilogram spacecraft shot into this asteroid, which allowed to deflect its trajectory around the primary system. That was absolutely exciting, and the good thing is that we allow the public to show that in live, to see that in live, and therefore the public discovered with us the first images of this asteroid, which I think is very important. To have the public support, you need to make them participate with us, and this was exactly the case. We were as ignorant as the public before we saw these first images. And then afterwards, we got these images by an Italian CubeSat, which shows the poor Dimorphos, which we were not sure was still existing afterwards, but it's still there. And we even created an active comet. You see here the tails, which goes about several tens of thousands of kilometers from the asteroid. And there's still a faint tail going on. These are the ejecta from the impact. But there are still some questions after the DART impact, which of course is, what is the final state of Dimorphos? Because we don't have images of Dimorphos afterwards once the ejecta were removed, and therefore we don't know if we left a crater or if we entirely reshaped the object. Both possibilities exist according to the data we have. What are the properties of this object? Is it a monolithic rock, or is it an aggregate, like, agglomerate of boulders linked together by gravity? And to really understand why Dimorphos behaved as it behaved, we need to have this knowledge. And finally, what is the actual momentum that has been transferred by the impact? So you bring the momentum of the spacecraft, and then you transfer it to the target, but the ejecta take momentum away, and this momentum added to the momentum of the target. And in order to measure that, you need the mass of Dimorphos, which obviously needs another spacecraft. So this is where the next mission by Europe comes, but I should go back in time because everything started in Europe in early 2000, so it's not that fast. When ESA created a panel that recommended a mission which was called Don Quixote, which was actually a projectile called Hidalgo at that time, so now Hidalgo is another problem. And the probe which is orbiting, called Sancho, so the aim was to have Sancho arriving first, observing, characterizing the asteroid, and then the projectile coming, and Sancho measuring the deflection. So this mission went into phase A at ESA until 2007, so it went quite fast, but unfortunately there was no budget and program associated with this kind of mission at ESA, so it went into a desk. So most of the time is due to the fight for the approval of a mission. Once the mission is approved, it goes faster, as you will see. So in 2011, actually, because this mission was mentioned in all the reports on planetary defense, even at the White House level, so we had a planetary defense conference in Bucharest, and with, I should say, Cheryl Reed from APL and Andy Chang, we started to discuss again this and see, and this is where international cooperation can help. How can we do this mission together? How can we share the effort between the two agencies? And therefore, we also brought some other people, Jan Carnelli from ESA, Michel, who is also in the room, and we started to have a technical agreement involving ESA, APL, which is taking care of DART now, Observatoire de la Côte d'Azur. Secondly, a report in 2012, so only 1 year, where we started to make the mission requirement for these missions. And then the first team setup of this cooperation, which is DART, and at the epoch, the HERA mission was called AIM, for Asteroid Impact Mission. So you see, within 2 years, we were able to set up a formal scheme between Americans and Europeans in order to develop this mission, of course, based on the idea of the Don Quixote concept. And the first design was having a European spacecraft arriving before the Americans, which is rare, but it happens, to characterize the binary system, then let the DART impact occurring, and then going to measure the outcome immediately afterwards. So that was the concept, which was really nice. However, at the Council Ministerial of 2016, we were not approved. So again, the mission could have been faster in our scheme, but the approval was not there. But fortunately, because, as I was saying, the interaction, which was really continuous between the engineers of the various industries and the scientists, we were really able to optimize quickly the mission so that we could propose a new scheme, which is now the HERA mission, which eventually was approved in the Ministerial Council of 2019 for a launch in 2024. So you see that from approval to launch, we have only 5 years. And this is why it's very important that we work as a team, including both the technicians, the engineers, and the scientists. And we had the first face-to-face workshop in Nice last year only, because of course before we were all seeing us in 2D via a screen. And that was really a great thing to see everyone. I insist on the human aspect because for me, space missions are human adventures, and you need to have a great cohesion of the team and a great atmosphere. And really, when this is the case, it works perfectly. So we have now this revived IDA collaboration, where this time DART impact occurred, and now HERA will arrive in 2027 because we launched in 2024. So in total, 16 years since 2011, which could have been 11 years in total, including HERA, so AIM and DART, if you were approved in 2016. So basically what we're doing is quite fast, even though it took time because, of course, you need to get the budget. And that's part of the space business. So it's quite good, and you can see here the international cooperation with all the Americans and European working together. So the HERA mission now is we are there at this stage in 2023, and we have a launch on October 2024 at Canaveral with Falcon 9. It's of course very challenging to develop a spacecraft in such a short time with 2 CubeSats, because in fact we have a mother spacecraft and 2 CubeSats. So that's where I say that the use of CubeSats is really nice because, okay, it's not so simple, but you accept more risk because they are cheaper than a mother spacecraft. And we have one spacecraft that will study the composition and the dust environment of the system, and the other CubeSat, which for the first time, we measure the internal structure of an asteroid. That's never been done before with a radar on board of one of the CubeSats. So this is a scheme that I think is great because you have both a mother spacecraft and 2 CubeSats that can do closer proximity operations and take more risks. So this is the mission scenario where there will be a lot of firsts. This is the first rendezvous with a binary asteroid, the first radar tomography, the first full-scale cratering experiments entirely documented with the HERA mission to validate the impact models, and the first deep space CubeSat for very close asteroid inspection. Now, next step after that would be how to do something fast, because at the decadal survey of NASA, for instance, there is a suggestion that we should do a rapid reconnaissance mission. Like, let's say an asteroid comes to us, we know it very late, and we want to send a precursor mission to tell us what it is made of. So we have to build it rapidly. So one idea is to use Apophis. Apophis is incredible. It's a 400-meter object that will come at 31,000 kilometers from the Earth on April 13th, 2029, which is a Friday the 13th. So it won't impact the Earth, we're sure of that. But in fact, you will experience possible surface motions because of the tidal forces that Earth will experience on the asteroid. So nature offers us a great laboratory to study surface changes, surface modification, by this encounter, which is just once in a lifetime. And in Europe, you will be able to see the asteroid with a naked eye. So the light will be seen. So how wonderful will it be to have children and tell them, you know, look at this little light. We have a European spacecraft being there That would be fantastic, noting that the OSIRIS-REx mission that will return samples from Bennu in September will go to Apophis, but arrive 7 days after the encounter, so we won't see the surface changes. So having both a spacecraft that comes before and during the passage, and then another one afterwards, is a great synergy between US and Europe, and also a great thing to really study these very, very counterintuitive mechanics of asteroids. So to do that, an idea is to refine a platform of HERA. So HERA will launch in 2024 if it behaves correctly. Why not using this platform and CubeSats in order to go to see Apophis, which is challenging because 2029 we need to launch in 2027 or something. So we have to build fast, and that's where I say leveraging of past platform that worked is very good, and we have this Ramses concept study at ESA currently, which idea effectively to use the same platform and demonstrate the feasibility of a rapid reconnaissance mission, which, as I said, is aligned with the decadal survey of NASA. And also, if we can demonstrate it works well, that opens new doors to do faster missions. Another idea is to have international corporations at the level of 2 agencies, or 2, let's say, one agency and one component, JPL, for instance. And we have this other study of an Apophis mission. There are a lot of motivation for Apophis currently with JPL and CNES, which is to do, again, to have CubeSats doing a bistatic radar tomography. So we go to see the interior of Apophis and see whether we see small changes during the encounter, which is another idea, quite fantastic, and also could be a good demonstration that we can do something fast if it happens. So this is another kind of examples. So this is what I wanted to say. We have possibilities to reuse platforms. I think it's very important that engineers and scientists work together, and that we accept more risk because we do more missions. And because I talked with some young people yesterday that remind me that I had a crazy video of what happened when the DART impact occurred, since being ridiculous doesn't kill, I'll show you what happened. This is during the DART impact. So we were in autonomous navigation, nothing to do. All the DART team came in this room, and these are the last moments. So we see the images on live. We discover. It was really real. And this is it. Okay, so you see, these are why we do this. Thank you very much.